Welcome again, everyone, to our OpenSim webinar. My name is Jennifer Hicks. I am the R&D manager for the OpenSim project and the Associate Director of the National Center for Simulation and Rehabilitation Research here at Stanford. And I'll be serving as the moderator for today's webinar. I'm pleased to welcome today's presenter, Daniel Jacobs, who's joining us from the University of Michigan. Next slide, please. So just a quick reminder of what OpenSim is. So OpenSim is a freely available software application that allows users to visualize musculoskeletal structures and simulate movements of humans and animals and robots. The application includes tools for general purpose inverse kinematics and dynamics. You can perform an optimization to estimate muscle and joint forces. There are methods to create simulations that track motion capture data. And then there are tools that allow you to analyze and visualize the results of your simulations. So the first goal of our webinar series is to showcase cutting-edge research that's being performed with OpenSim. OpenSim is also a growing and geographically diverse community of users. So the second goal of our webinar series is to provide an easy platform for the OpenSim community to communicate and collaborate and learn more about what OpenSim can do. Before we get started, next slide. I have a few reminders about the webinar format. So questions will be addressed at the end of the presentation using the Q&A panel, which you can find on your WebEx controls. If you need any additional technical help, you can also consult the guide on our website. Next slide. So with that, let's dive in. I'd like to introduce our speaker. So Daniel Jacobs is a postdoctoral fellow in the Human Neuromechanics Laboratory that's led by Dan Ferris in the School of Kinesiology at the University of Michigan. In his current research, he's using novel sensing and control strategies for actively powered exoskeletons that are intended to assist push-off and minimize the metabolic cost of walking. In 2013, he received his PhD in mechanical engineering from Stanford, and he was also a postdoctoral fellow in the bioengineering department here at Stanford and worked directly with our OpenSim team. I'm very excited for today's webinar. Dan is going to give us a great introduction to using the OpenSim API or set of libraries in Matlab. He'll use it to build and edit models. His webinar will also really help you understand what's going on underneath the covers in OpenSim. This is our first webinar that's going to allow you as listeners to directly participate. Dan will tell you more about this once he gets into his webinar, but you'll have the chance after the webinar to build your own dynamic walker and submit a video of it in a friendly competition. So with that, I will pass the mic over to you, Dan. Take it away.
All right, thank you very much. I want to thank everyone for attending today's webinar on building and editing dynamic walker models in OpenSim. I really hope today's presentation will inspire you to build and share your own models, not just walker models, but other interesting models with the OpenSim community. So let's start by talking about So if you're familiar with OpenSim software, you know that it comes packaged with an excellent set of musculoskeletal models. But if you're like me, you might want to know how can you extend a model with mechanical components for your research study. For example, you might want to investigate powered plantar assistance on the metabolic cost of walking. Or you might want to look at an orthotic design to see its effect on limb excursion for an injury prevention study you do. And to extend a model, we really need to understand what an OpenSim model is. How do we create it? How do we edit it? And that's really the goal of today's presentation. So our example today is on a dynamic walker. So I have a short video of the simple walker that we're going to create today. It's a planar walker. It's passive. It has knees and curved feet. And those curved feet are helping keeping the stance leg fully extended. And those feet are welded to the lower leg. So even though we're talking about a dynamic walker, everything that we talk about today is going to apply to model building in OpenSim in general. And today's talk, there are 4 sections. The first is building the actual walker model. In the second, we're going to talk about how you can make smaller scripts to add model components easily and programmatically through the new Matlab Scripting engine. In the third section, I'm going to highlight some of the model editing capabilities of the GUI and set the stage for you to modify the basic design we're going to create today. And in the last step, we're going to discuss how do you run forward simulations and how can you use this Matlab scripting interface to link your model to perhaps your own simulation and optimization algorithms that you use in your lab. I want to point out that because of the format, some of these elements might move quickly, but the slides as well as this presentation will be available on the OpenSim website. This video will be posted to the OpenSim YouTube page, and the files it will show are also on the main simtk.org page, so that you can follow along at your own pace later. So today's example are passive dynamic walkers, and they actually have a very rich history. So going back to sort of the late 1800s and early 1900s, toy makers established several patents for robots, or for toys rather, which would walk passively if pulled by a small weight or put on a small slope. And these toys inspired Gear in the 1990s to investigate passive dynamic walking in larger robots. And the idea is if you can understand the natural walking dynamics of robotic systems, you may be able to improve the design and reduce the control of modern robots by allowing the dynamics to accomplish a large part of the locomotion and adding smaller motors, say, to raise or lower the feet. You probably, if you haven't seen a passive dynamic walker, you might have played with a slinky and a set of steps and seen the ways in which small amounts of gravity can create periodic motion in different systems. So on the left, we have a still from Gear's video. As you can see, that is the model we're trying to build. And on the right, you have the actual model we're going to build today in OpenSim. So let's really dive right in. The first thing I want to show you is actually, let's open up the GUI. And inside the Dynamic Walking Starter archive on the website, there's a folder called Models, and we have several models in there. So I'm going to open up our basic model. And this is the model we're going to talk about first. As you can see, it has no feet. We're going to add those later. But on the left-hand menu, I just want to show you some of the components in the Navigator menu of the GUI. Inside our walker model, we have a series of bodies: the ground, the platform, the pelvis, the thighs, and the shanks. We have a set of joints. We have contact geometry, which is actually going to allow us to describe the ground reaction forces in the model. And in forces, you can see we have those contact forces as well as joint limiting forces. So there are lots of elements in the model. And so I want to highlight some of these components in order to give you enough insight to build your own models in the future. So this model is a set of components which is going to describe all the elements of the physical system. There are the individual elements, their mechanical properties, their geometry, there are the connections, not just joints, which will give us additional mobility relative to bodies, but constraints, which actually take them away, and those interactions, the forces that we talked about. And so the model really is an organizational layer. We're not going to do computation at the OpenSim model level. We're going to pass that information down to SimBody, which is the computational layer that provides the multibody dynamics engine that actually does the work of our simulation. What I do want to highlight is some of the key components. So if we're going to build a mechanical system, we need to understand what a joint is. in OpenSim's terms? Well, a joint defines the relative mobility between two coordinate frames on two bodies. So if we have our parent body, which is the thigh here, and we have a child body, which is our shank, the joint we're going to create is a pin joint. And that's going to be a 1 degree of freedom joint. And so in this system, it's going to be described with a single generalized coordinate. And that's going to help make this, or make the simulation of these systems more efficient. An alternative way of forming your equations of motion is to treat every rigid body in 3D space as having 6 degrees of freedom, and then either augment your set of equations with 5 additional constraint equations, or use those 5 equations to eliminate variables. So let's take this great figure and actually look at what the system looks like. So on top we have a thigh segment. We have X and Y axes that are fixed inside that body. We have an origin of our thigh, T0, and then in red we have this pin joint we're trying to create. So the pin joint has 1 degree of freedom about the positive Z axis, and that is pointed out of the page towards you. On our lower body, the shank, we have shank axes, X and Y, and its own origin. So if we're going to describe this joint, we need to be able to describe the location and orientation of the joint axes, the joint coordinate system, relative to the thigh body. So you can see on our thigh element, we have no change in orientation between the black and red Y and X axes, but we need to move from our origin T0 down to the pin joint. So this would be minus half of the length of the thigh in the Y direction. Similarly, to describe the joint from the shank's perspective, we're going to move positively in the Y direction by half of the shank's length. And again, there'll be no change in orientation. So if we have these 4 elements, the location and orientation of the joint relative to each body, we can then build a joint in our system. So what is our model? It's really essentially just a collection of bodies. It's a planar model, and then we are adding weld and slider and pin joints to our system. So with our model, we can actually go back and do. And now under the top menu of window, we can open up the topology view, and that's what we have on the right here. We have a ground body, we have platform, so each one of the outlined rectangles is a body, and then each one of the arrows going through the point is our joint. So for example, this L thigh to pelvis joint is our left hip, connecting the pelvis to the left thigh, and then this L shank to L thigh element is our knee because it connects the left thigh to the left shank. Now we've made one interesting choice which I want to discuss, namely we've created the planar pelvis joint, which has 2 degrees of freedom in translation by assembling 2 1 degree of freedom slider joints. And again, that gives us some computational efficiency because we have less generalized coordinates inside our system. In order to get translation in the X and Y direction, we change those components we talked about with our joint so that the orientation of the joint is different depending upon whether we want to have a X translational degree of freedom or Y translational degree of freedom. Another key element of our model are forces. The figure on the right shows the 2 different contact geometry objects that we're using in our base model. We have spheres on the feet, on the knee, and on the hip. And we have a contact half space that's on the platform. And so if we now define a contact force, we'll say that a force, which will be the left ground reaction force, exists between the left contact sphere and the contact half space of the platform. The geometry by themselves don't interact with each other unless there's a force defined. And so one tip when you're defining your half spaces is notice that it's describing the approach of the opposite body. So the arrows point downward because that's how the contact spheres will approach this surface as opposed to representing the normal of the surface. So what's in a model file? Well, underneath OpenSim, the model is actually written using XML, which is an extensible markup language format similar to HTML. And there's actually several ways to create an OpenSim model file. You can use a text editor to actually write these elements in XML. You can use the API to write a model in C++. We're going to talk about the third way, which is to use Matlab Scripting to write a model in MATLAB/Java. A few standard conventions will be helpful as we start to dig under the hood and look at some of the scripting code. There are standard conventions, so we'll pass in numbers and it will be assumed that we're in SI units, where that's kilogram, meters, seconds, and radians. There are some examples where we might ask for a system in degree, for example, in the contact limit forces. And opening up an OpenSim model and actually looking at the comments is really what's going to help you make sure you're providing the model with the right units. There are also great function conventions, set, get, and update, as well as add prefixes that will help us as we find files. So as we dig into the code, we'll talk more about the differences between some of these. So let's add a body to this model. Well, there are 5 steps to actually add a body to the model. The first is we have to create a body object and set its properties, things like its mass and its center of mass location. We have to create the joint object that links our new body object to a parent body already in the model. So we have a ground to start. We link the ground to the pelvis to the side to the shaft, and so on. If our joint that we create has coordinates, for example, if it's a slider joint as opposed to a weld joint, we're going to need to name those coordinates so we can see them in the GUI. We're also going to add a visualization object so we can see something. And finally, we add that object to the model. So I'm going to highlight some elements of the file create walking model and environment.m. It's in the user functions folder in the provided slips, or the provided archive. And we're going to just highlight one of the joints of the model. But if you understand these 5 steps, it's really just repeating them over and over again to assemble your full model. So we want to set the body and its properties. But if you've never written it before, you can imagine it'd be very challenging to figure out exactly what functions are available. Luckily, there is a very easy way to examine the functions of OpenSim. If you go to the GUI and open up Help, you can click on Doxygen, which is an automatically generated set of documentation for each build of OpenSim. So here is the Doxygen for the OpenSim that we're using. And we can click on these individual elements to look at different components of the system. We can also search using the upper right, but because body is such a key component, there's a nice link on the main page to see what's inside the body. So if we click on that link to a body, we're looking for the public member functions. And you can see those very useful prefixes we talked about right away. So there's add display jump. We can get and set the mass. We can get and set the mat center. We can get and set the inertia. So if we're going to create the pelvis, we need to create a body. There are several constructors of variable, and then we could use the set functions to change its properties. So that's exactly what it takes to create our model. We create a new body. We give it the name pelvis. We set its mass to a variable inside the MATLAB workspace called pelvis mass. And then we set the inertia using the provided inertia constructor that's built in the scripting language, where we can pass in x, y, z moments of inertia, and then the off-axis products of inertia. Creating joint objects is our next step, and as you can see, we have variables that are vec3s. These are 3-element vectors that describe the location and orientation of the joint in the parent and the child, as we discussed. Now, location's an XYZ component of a position vector, for example, in the parent body, a position vector from P0 to P. But the orientation, it is a three-element vector, but these represent X, Y, Z Euler angles describing the rotation of the joint axes relative to the parent. If we want to create a slider joint, we can go back to Doxygen, type in slider joint. And again, looking at the public member functions, we can see there's a long constructor that involves the name, several bodies, a parent and a child body, and then it takes several FEC3s as well. So once we've created our joint, we need to actually take the degree of freedom and give it a name. And here's the difference between get and update in OpenSim. Get gives you a non-editable version of the information. So if you can imagine, I just want to know how far my pelvis has moved. I'll use get because I'm not going to change that information. I just want to use it to do something in my controller. In this case, where we actually want to change the properties of that coordinate, we're going to use update underscore coordinate set because we're going to get an editable copy of that information, and then we're going to set its range being 0 to 5. We're going to set its name, pelvis TY, that's going to appear in our GUI, and then give it a default value. Lastly, we're going to add visualization. We add the body to our model as well. So we have, OpenSim has a large set of basic models. You can use any object you want in OpenSim if it has the extension OBJ, VTP, or STL. In this case, we use the built-in sphere, and then we use the displayer to scale it so that our pelvis width is the long axis, and we have shortened ellipsoid axes. Lastly, we add the pelvis massless body to our OSIM model. And at this point, we have our platform and our pelvis in the figure on the right. All this information is stored in the objects, and you don't have a model file until you call the last command, which is print. So we're going to print something called walkermodel.osim, which is OpenSim model file, to our model directory. So if we open up Matlab and we open up this create walking model and environment function, there's a place at the top for you to change model parameters like the platform length, the pelvis mass, and so on. You can change whether or not you want terrain or not by basically changing the add obstacles variable. The code that we discussed today is adding the pelvis, and you can see that it's very similar for the left thigh and other elements as we go on down. So we run this quickly. It really takes under a few seconds. It's already done. And now in the model folder, I have this new Walker model terrain that I can open in OpenSim. So I'll close the topology view here. I'm still going to use the base model for the moment. And I want to talk about now how you can run a forward dynamic simulation in the GUI. One way to do it is actually to open up the Tools menu, select the Forward Dynamics tool. That'll give you a lot more options, the ability to load in initial states file, add analyses, and other key parts. But we just want to see this model move. So we can actually use this running man. If we click on the arrow, we can change the end time. I've had it set to 2 seconds. And now when we click on the running man, our model simulates and actually moves so quickly we can't see everything that happened. On the right side of the top menu are the movie control tools, and we can change the replay speed. In this case, I'm going to set it to 1/4 and then run our model. And as you can kind of expect in this passive model, our model is just going to collapse. It's held in place here because I have that knee limit actually, and it stops it from falling. But that's not enough to keep the leg together in stance. So how do we actually improve this model? Well, if you don't have any components to hold the knee in place during stance, the stance leg of the walker is going to fold. So we want to learn how to extend the model by adding components. Two examples are provided in the setup files. The first is adds a magnetic force between a point on the thigh and a point on the shank. The way that we're actually going to use today is we're going to replace the spherical feet with curved cylinders. So I've created a model of feet using an open source tool called Blender. You can use any program you want, provided again it gives you an OBJ, STL, or VTP file. So I won't dig into the code here, but the steps for adding a contact object are very similar to adding a body. We first create the object, we add that object to the model, specifying where the contact geometry object is relative to the body. For example, if I want a foot contact sphere, I need to say that it is at the bottom end of the shank segment. I'll then create a force object. For example, there are two types built in OpenSim, a Hunt-Crossley object or an elastic foundation force. And you specify which contact geometries will actually create those forces. Lastly, you add the force object to the model. The example of adding custom feet to our model is the add custom feet.m script file in the user functions folder. So in this section, I want to highlight how you can use the GUI to adjust the model. As you're building your walker, there are several model parameters which are likely to change. You might, for example, change the mass, center, mass location, and inertia of the body. You might want to change the slope of the surface or the location of the curved feet or whatever feet you've created relative to the shank. You can lengthen or shorten these segments by moving the joint locations. You can adjust the forces, for example, the joint limit forces. You can change the range. When do those come on? You can change the stiffness and damping of those actuators when they are on. You can also adjust the contact stiffness and damping of the forces. So I'm going to show you how quickly you can adjust the slope of the model in the GUI. If we open our model back up, we scroll up to the bodies menu, and now we can look at the platform. And you'll notice as I click on the different elements inside the navigator, the elements of the properties window changes. So on platform, or I'm actually say pelvis, I can change the mass center location, which is a nice 3-element vector here, as well as the inertia. If you select platform to ground, you see the orientation and parent here, the parent being the ground itself. So we've rotated this at -10 degrees, or roughly minus 0.17 radians. If I want to double that to roughly 20 degrees, I can put in -0.35, and you can see that the slope of our model has changed. So as you edit your model, I'd recommend definitely saving the model as, giving it a new name, so that you can keep track of all of your different changes. So some design tips and tricks. Well, most likely, if you've ever tried to simulate multi-body systems, you run into cases where your simulation starts to slow down. And simulation slowdowns can be the result of high-frequency vibrations in the actuators. So running our simulation saves the states of the models, but perhaps you want to look at the forces occurring in the model as well. Well, one way to do it is use that forward tool we discussed, add a force reporter analysis, and look at the contact forces and joint limit forces to see if you have these vibrations occurring. Another thing to keep in mind is that the stance leg acts as an inverted pendulum and the swing leg is a free pendulum, so you can adjust the frequency of swing by changing the center, mass, location, and leg length. And the goal is to really try to avoid scuffing of the swing leg. You want the leg to essentially be perpendicular to the ground or close to it so that you have the maximum amount of clearance for your swing leg to push through. You can also adjust the energy addition in your walker by adjusting the platform angle and the contact parameters. For example, you can change the stiffness or change the damping of the contact force as well, and that's also going to change how much energy is lost in each step. The last part I want to talk about is really how to go from here. Iterating through a large set of parameters is challenging, and as you probably imagine, I didn't spend all of my time hand-tuning that video I showed before I used to optimize it. Well, the Matlab Scripting engine can help you search the parameter space by enabling you to apply your own custom optimization to an OpenSim model. And to do this, you can use the provided integrate OpenSim plant.m function as a starting point for interfacing with your own scripts. Because that function is complex, I want to take some time to talk more about the multibody system and what that function is doing. So I'm going to expand on that diagram. We have our OpenSim model, which we understand now. But that sim body model actually has its own set of components. And one of the key components in that multibody system is the state. So you can imagine the state is a way of getting information out of the equations of motion. Your model will specify the initial state, and SimBody's job is to take that state and pass it to the integrator you've chosen and advance time and update the state after each completed step. That state information is useful because now you can say, okay, for that state, I want to now know what is the position of the pelvis in the state, what is the angle of the knee in that state, because perhaps maybe I want to write a phase-based controller, some other controller to try to help my system or help my optimizer function. So when you're now interfacing your model with OpenSim using this integrate OpenSim plant, we are basically separating the state from the integrator, and that's what I'm calling the planting. The example of this is in the user functions folder. There is a script file called main walker forward sim, and there's one with controls as well. So our model, we set the initial coordinates. We create a stamp by calling model init system that moves us down here. And now we have our state information. We have position, velocity, which we use, and actuator parameters. So for example, if you add a muscle to your walker or to whatever system you're building, the actuator parameters would be things like fiber length and activation, which are used to calculate the forces for your equations of motion. So the plant really just accomplishes one simple task. Its job is to get a state either from the model or the integrator, because the integrators move time forward, and its job is to pass out y dot, or basically the state derivatives. So what this function does, instead of passing this state information to OpenSim's built-in integrators, it allows you to pass it to the integrator of your choice inside Matlab. So this could be ODE 45, or in the examples provided, ODE 15S. And very similar to the GUI, you can visualize these tools. You can write controls, for example, a PID control on the knee. That's the example that's provided. And you really have the freedom now to interface your model with your integrator and your optimizer because you have this plant function. So how can you get involved in our community? Obviously, this is something that is very fun, and it's a key part of what we try to do with these webinars. Well, you can take a video of your walker quite quickly. So I'm going to load in a model and a set of states that I have run before using a forward tool. And you notice I dragged both of those directly into GUI. That's a very nice and fast way to open your file. And now on the right side of the view are a set of tools that control the various views. But there's also this very nice icon of a camera that's going to let us save a movie. So if I want to save a movie, I can control the speed, whether it's real time or half time, with these upper menus. I can change where I see in my movie by zooming and moving the screen around. This view window is essentially the frame that's going to get captured by the video. So if I shrink it, I'm going to get different sizes of my video. And so we'll zoom in and take a few quick steps. So you click the movie icon. It's going to save this to our model folder. We'll call it a few steps. We'll hit play on our video. It's going to take these steps in a quarter time. I'll stop it, and I'll finally stop the video by clicking the camera icon again. And now I have this lovely video called A Few Steps. And I'm ready to submit this to YouTube. So as you get started, the walker, we are hoping that you'll join our OpenSim community and exchange tips, script files, ask questions of each other on the OpenSim community forums. And lastly, as Jen discussed, we're hosting a very friendly competition. If you upload your video to YouTube and email the link to opensim@stanford.edu, we will be sending out OpenSim t-shirts to some of the best entries. So I'd like to thank you all for participating, and please start sending your questions to the moderator.
Thanks, Dan, for a great talk. Now we'll go ahead and get started with the Q&A session. So all of your questions will be text-based. So you want to find the Q&A box on your WebEx controls, and then type in your question and make sure you select to ask all panelists. Hold on one second. I also, we have AJ Seth joining us as well. He's the lead OpenSim API architect, so he's here to help answer questions if we need him to. So with that, I'll go ahead and open up the floor to questions. Let me see if any have come in so far. Okay. So the first question is from Dan Simon, and he says that he saw we were using OpenSim 3.2, and he wants to know when that will be released. I'm probably a good person to answer that question. So OpenSim 3.2 is currently available as a beta release, and we've already done a fair amount of testing on that, so it's pretty stable. So you can find the beta release if you scroll down on the OpenSim downloads page, and you'll get the one that corresponds to your version of OpenSim, or the version of your machine, so 32-bit or 64-bit. And we should have the official release out by the end of the month. So hopefully that answers that first question. And you guys want to make sure you grab this beta release of 3.2 for your for doing the dynamic walker demo. Okay, so go ahead and get your other questions in. While we're waiting for other people to ask questions, I'll ask the question that seems to come up fairly frequently, and that is, if I build a model in a CAD program, can I import that into OpenSim? Are you there, Dan?
Yes, thank you. Hope you can hear me now.
Yeah.
So there have been some users who have tried to automate that transition from CAD to OpenSim. And as far as I know, there's nothing in there directly that lets you do that. But as you saw for the contact mesh with the foot, there is a way to import small objects. So I would say if you have a linkage or some other element that you really want to use as a body, you can definitely import that if you have an object file. But in terms of a full automated system, that's something that's still in progress. And if you or any participant wants to move that along and submit it, this is a great way of getting involved on the forums.
Okay, yeah, thanks, Dan. And just to follow up and clarify a little more, so you can import the OBJ file that has the geometry of the object that you're interested in. And then you will still have to recreate the linkage or any inertial parameters of the model in OpenSim to match your CAD model. But like Dan said, if you want to work on an importer to do that and contribute it to the community, we certainly encourage that. Okay. We're still waiting for audience questions. Make sure you get your questions in so that you can win the Dynamic Walker competition and get an OpenSim t-shirt. I know you all want one of those. But while we're waiting for more questions, I'll ask another one. So you did show some tips and tricks for getting started. Since, I mean, I'm not super familiar with building dynamic walkers, and many of the people in our audience may be in the same boat. What do you think is a good first step for getting started and building a stable walker from the different tips and tricks that you showed?
I think really the key element is to settle on your strategy, your specific strategy for keeping the leg locked during stance. A lot of what you might choose for your link, mass, and inertia parameters is going to really depend upon that element. And so there are lots of papers that definitely start with Tad McGear's work and branch out from there, but the curvature of the foot also becomes very important. So you can imagine you're taking this step, you have the inertia of your body rotating over your curved element of your foot, and that has a certain period. And now you have a free double pendulum with your swing leg, and it really needs to match that period so that your knee is bent, your leg swings through completely without scuffing before it locks on extended for the next stance period. And it's much easier, as you saw in the GUI, to change those mass and inertia parameters of the model. What you can do is change the contact mesh of the foot. If I wanted to go from a cylinder with radius, say 50 millimeters to 100 millimeters, I would need to go make a new file, import that instead of the one that's in there. So I would say if you're going to use curved feet or some other element, to design those first and then adjust the model parameters in the GUI later. That's probably the easiest way to get started.
Okay, great. Thanks for those tips, Dan. I see that somebody has raised their hand in the WebEx controls. You need to go ahead and type your question into the Q&A box, or you could even put it in the chat box if you can't find the Q&A, and we'll answer your question. In the meantime, Dan, can you show us, okay, so now I'm ready to get started. I have your tips and tricks. Where do I find all of the materials? Where is that? I think you mentioned the Confluence page. Can you show us where that is and what's on there?
Yes. So let me just start up. I called it up earlier, but simtk.org on the main site. There's the link to OpenSim 3.1 right in the middle of the page. On the right, we have OpenSim, OpenSim models and examples, and OpenSim release betas. The release beta is where 3.2 update 4 is, and again, you can select whether it's 32-bit or 64-bit to match your Matlab version. And the link to Confluence is actually on this very lovely first page. So we're going to go ahead and I will copy that link out for a sec. Take us right to the page. And on that page, there's very helpful links. There's a link to download OpenSim again. Close these windows in case they're on the screen. There's a, in the past, people had to manually configure their Matlab interface. There's a very nice script function, configure OpenSim.m, that's in the script/Matlab folder of the directory where OpenSim is installed. And if you run that, it'll adjust the paths for you to make it right. The dynamic walker files are also on the home page of OpenSim. So on the right, you can also come down to the OpenSim models and examples. And this dynamic walker starter.zip has all the files you need. We only talked about a few of them today, but on user function, you can see that there's a good number of scripts to help you get started. There are examples of adding a set of different components, a muscle component, a path actuator, a clutch path spring. There are the integrate and create walking model files we discussed today. There are also some small scripts that I've used to help you get started plotting and reading OpenSim data. And finally, there is the curved foot object that we use in the model, this thin half cylinder.
Okay, great. Thanks, Dan. And we'll go ahead and we'll include a link to that Confluence page that compiles all this information. You'll get that as a follow-up email. Should be sometime tomorrow as a follow-up to the webinar. Okay, we have another question now from the audience. This is another question from Dan Simon, and he's wondering, is there any module specific to product design for OpenSim?
Not that I know of. It'd be helpful if you could describe to us what you mean by module, what specific functionality you're looking for.
Yeah, I can. Well, maybe Dan, you can write in some details. There isn't a specific module to product design, but you can currently create a big set of bodies and controllers and actuators in OpenSim, so similar to the process that you'll use for creating a dynamic walker. And that you can currently do by editing XML files or by using the OpenSim API in Matlab, like Dan talked about in the webinar, or in C++. We're in our development timeline over the next year or so. We are working to try to make it easier for people to build models by having a better toolbox of model components that people can use to make the scripting interface for building models easier to use as well. And we're also going to start to add model building features in the GUI so that you can add, say, a new, the foot for your dynamic walker directly in the GUI without having to edit XML files or use the Matlab scripting. So hopefully that answers your question. I think the short answer is that yes, you can do product design in OpenSim, and we hope to continue to make it easier to do by making those improvements that I just talked about.
If there's time, I mean, I could give a brief overview of optimizers too, if there's no follow-up questions.
Sure, yeah. Oh, wait, here's a question. Let's see. So this is a general question. This is from Julia Nichols. She's fairly new to OpenSim. What kind of resources are available to get up and running? So we have a big set of examples and tutorials that are also on that Confluence page that Dan showed. So you'll see on the left-hand side, up a couple, there are examples and tutorials, and those run from introductory to advanced. And so working through those examples is a great way to get started. And then after those, you've done those, then as a next step, we have workshops for people who've already learned how to use OpenSim that we have about twice a year. And we also have a visiting scholars program as well, where researchers can come work with the OpenSim over the summer for about 5 weeks. So yes, there are lots of resources to help you get started. And so now we have a comment from Alex McIntosh, and he said that a brief overview of optimizers would be fantastic. So yeah, if you're up for showing that, Dan, we still have some time.
Okay. There are examples. First, I just want to show what's provided with OpenSim here. So if you go into your OpenSim, you go down to the SDK here, there are examples. They are for the API, but I believe there's an example in here now from Matlab as well. That will give you some more overview in addition, or some more overview of optimization. There are also things that we did discuss, like the OpenSim manuals and the SimBody API guide that talk more about optimization. But just from the sort of design perspective, let's talk about probably the simplest optimization you can do. So you can create a model, and let's say we wanted to search the space of just initial conditions. So speed and velocity. So in the GUI, you have this coordinate menu, and you could go in here and manually change the values of the pelvis and hip and knee and give them speeds and try to get to a point where your model walks stably. But if you even look at just videos of these walkers in YouTube, there's sometimes a little bit of an art to just getting it launched properly. So probably the most basic optimizer you can use is the most basic objective function you could use of an optimizer is probably just forward distance of the pelvis. There's problems with that which are great places to ask on the forum, but you can imagine I want to change my initial properties and just keep looking at how far the pelvis travels and then figure out what my best set of starting conditions are. So when we talked about this state, this loop is very similar to what you do. You'll create your model, you'll have a plant and an integrator, whatever you've chosen, whether it's the built-in OpenSim elements or your Matlab private code, and you run a forward simulation. At the end of that forward simulation, you get that state out, and now the coordinate you're looking for is pelvis TX. So you'll call a get value on that. You say, okay, how far did I go? All right, that's my objective. Let me try my new set of coordinates, run another forward dynamic simulation, and you loop that around and around. So really your optimizer, your basic optimizer is just taking this forward dynamic simulation and changing whatever parameters you want. The example was coordinates, but you could easily change masses and inertias or other elements, and keep looking for your objective function. So if you're doing design elements, or if you want to do something that was like maybe a product design optimization, you can change those elements of your model, run the simulation, and wrap this very fast optimizer around it. So hopefully that helps give you some more information. And I'm definitely available and will join in forum discussions if you have more questions in the future.
For you, Dan. We have one more question from the audience, and this is from Sang Lin. Is Matlab SimBody necessary to run this dynamic walker simulation?
So the model information is an OpenSim file. I mean, it's easy to read. It's not proprietary, but you'll need something that understands how to turn those tags that are just things like bodies and massive inertias into something that forms the dynamic equations of motion. Now, underlying OpenSim is SimBody, which is excellent dynamics engine. And if you have a background in C++, it's definitely great to write that API code.
I think maybe the question, Dan, was whether Simulate is necessary, and Matlab and Simulate is necessary. So I think to answer the question, not completely. You can use the GUI, that's free and open source. You could also, you can edit model files in XML, so you can use the XML browser in the GUI to find the markup for the component that you want to add and add it to the .osim file that way. We haven't done extensive testing of this particular example, but other users have started to try using Octave, which is an open source alternative to Matlab, and they have been able to call the OpenSim API like the Matlab scripts do from Octave. So that's something else you could try. Or if you're familiar with C++ programming, you can also do it in C++.
Thanks for clarifying. I appreciate it.
Yeah. I think we have time for one final question, and this is from Eric Dykstra. Is it possible to access the SimBody API via Matlab with OpenSim 3.2 beta, or is it still as limited as OpenSim 3.1? So we have added more access to SimBody in OpenSim 3.2 beta. AJ, do you know any of the particular things that we have accessed or added access to? I think we've streamlined the handling of SimBody arrays, for example, is one thing I do know. If you have questions about particular things that you want to access that you're having trouble doing, Eric, send us an email or post something on the OpenSim user forum. It would be great to get your feedback on what else you would like to be able to do in Matlab. Okay. Well, if there are no further questions, I think we'll go ahead and wrap up the webinar. Again, Dan, thank you for a great talk on what is a challenging topic. So the OpenSim API and scripting. It's always challenging to talk about things that are just text-based. So you did a great job of giving an overview of what's happening and grounding it with that dynamic walker example. If you can bring up the slides again, Dan, I just want to quickly acknowledge that OpenSim and this webinar series are supported by several grants from the NIH and from DARPA. So we have our National Center for Simulation and Rehabilitation Research, the SimBIOS grant, and the DARPA Warrior Web Project all fund OpenSim. Again, thank you all for a great discussion, for all the great questions. You can find information about the center, upcoming events, and other resources from the OpenSim community at our website. Please complete the survey that will appear in a pop-up window at the conclusion of the webinar. This will help us improve the webinar series and choose upcoming topics. Thank you for watching the webinar, and we really hope that you guys will try out the example and make a video and email it to us so that you can really continue your participation in the OpenSim project. So we look forward to seeing all your videos soon. Okay, thanks, Dan.
Thank you.